a lot less than here. So that bond is a lot weaker. Okay? We'll get back to that in a second. So what happens next is that the alkene comes along and essentially sits down, right? So the alkene is flat. So you can imagine this is my alkene, carbon, carbon. And these, the tips of my fingers, are the H's. So the H's are on the metal surface. And here comes the alkene. And the alkene simply sits down on the two H's and plucks them off. So what you end up getting is this, right? So these simply pluck them off and end up with the two H's attached on the same side of the molecule. Okay? So and you'll have the metal surface now free to pick up another hydrogen molecule. So this is kind of a cartoon that describes how the hydrogenation simply of the alkene occurs. The first step is the adsorption of hydrogen gas on the metal surface to create a complex in which the H-H bond is greatly weakened. The alkene, which is planar, comes along and simply sits down on the two H's that are protruding from the metal surface, sits down on two H's and picks them up and goes off. So you are then stuck with the H's on the same side of the alkene. Because they're on the same side, this is referred to as a syn addition. So it's clearly addition because we are destroying the pi bond and incorporating the elements of a simple molecule. That's how we define addition. And syn just means it's same face. It's happening on the same face of the molecule. So we get syn addition. That leaves the metal free to go pick up another hydrogen gas. So the metal then is a catalyst. Right? But, let me dive into that a bit more. What is our definition of a catalyst? Catalysts must have two characteristics. One is that they are not used up in the reaction. Okay? Well, here's the metal. The metal is engaged with the hydrogen gas. The metal is free to start the cycle again. So there's no net usage of the metal. That's requirement one to be called a catalyst. But what's the other requirement of a catalyst? And the answer is, it has to shunt the reaction along an alternate, lower energy pathway. Well, it does. Because if I try to react the alkane, and this is reaction coordinate, so here's my alkene. What do I have to do to get chemistry? I've got to break the pi bond, right? So the ascending portion of the plot is going to require some amount of energy to break the pi bond. The pi bonds are relatively labile. But if I also had to break the H-H bond in the normal way, that's not just a sigma bond, which is stronger than a pi bond. It's also a sigma bond with the smallest atoms that bond. So the amount of energy I have to put in to break that sigma bond would be significant. So my acquisition energy barrier for that reaction, right, to break both the carbon-carbon pi bond and the H-H bond, that energy barrier is going to be huge, right? That energy barrier is going to be huge because I'm breaking the carbon-carbon pi bond, which is not very demanding. The pi bonds are weak, but I'm breaking a very strong sigma bond. But that's not what we're doing here. What we are doing here is, yes, we're going to have to put in this, yikes, we're going to have to put in this much energy, right, to break the pi bond. That's unchanged. But now, the H-H bond we're breaking is not that one, it's that one. So what has happened is we've sent the reaction now along an alternate path because they are now making the catalyst metal complex. And what we have to do now is break that bond and end up with our product. So I have moved the reaction along a much lower energy pathway. Right? So I'm forming something new, there's a new intermediate, and the breakage of this HH bond is much easier than the breakage of the HH sigma bond. So by definition, this is acting as a catalyst. Now overall, I'm going to end up with a reaction that looks like this. I'm going to end up down here. Because we're breaking a sigma and a pi, and we're getting two sigmas out of it. Right? So I broke a pi and a sigma, and I'm getting a sigma and a sigma. Right? So if I break a pi and a sigma, and I get a sigma and a sigma, that's going to be an exciton. Okay? So the method is actually functioning as a catalyst by definition. It is shunting the reaction along an alternate, lower energy path. And it is being replenished at the end. It's not being consumed in the reaction. So this is an example of what we call heterogeneous catalysis. Because the catalyst, right, the metal, is not in the same phase as the rest of the matrix. So the typical catalysts, as we said, were nickel, palladium, platinum, typically absorbed on charcoal or asbestos. We will talk, there's a nuance here that we're going to get involved in more detail in the next lecture about the stereochemistry involved in the syn addition. That has consequences down the road. We'll leave it at that for now. Well, it turns out I can do exactly the same thing with alkenes. So I can start with the hydrogen gas. I can have my alkene come along and again sit on the hydrogen molecule. Okay? And that will happen not just once, it'll pick up one hydrogen and then pick up another one and give rise to your product. Okay? And so we can see that I can convert an alkene and an alkyne into an alkane by hydrogenation. Now, what we cannot do is take the alkyne to the alkene and stop. So do not by this method. There are ways of doing it, but not with hydrogenation. Hydrogenation, using the metal and the hydrogen gas, is pretty aggressive, and we'll do a complete hydrogenation. There are techniques that you will meet in organic too, where you can do a partial hydrogenation of an alkyne. That's not our concern for this course. So I can take an alkyne all the way to an alkane, and I can take an alkene to an alkene. So let's just explore that for a second, because there are a couple of ways that we can talk about this, for example, in an exam. And I can ask, you know, if I want to make butane by hydrogenation, draw a couple compounds that might be able to make butane. Well, I can start with one butene, it's hydrogen gas and catalyst. I can start with two butene, either the trans or the cis, right? And that will do exactly the same thing. Okay? Or I could actually start with a diene. This time I'll need two equivalents of hydrogen gas and the catalyst. Or I can start with an alkyne, right? Either the one alkyne or the two alkyne, right? So all of these would give rise to my product. So there are several different compounds. An alkene, monovinyl, right? Either that position or the C2, C3. or I could use a diene or an alkane. All right, and any one of those will give rise to butane on treatment with hydrogen gas and a catalyst. When you're hydrogenating two pi bonds, either over the same two carbons or not, it is customary to indicate that you're using two equivalents of hydrogen gas and a catalyst. I don't need you to tell me what the catalyst is. Once you say catalyst, that's good enough. If you want to say platinum or palladium, nickel, that's perfectly fine. Okay. Okay, so that's hydrogenation of alkenes or alkynes. Well, if you remember, we said there you can also make alkenes from haloalkenes. So method number 2 was from haloalkenes. And there are lots of ways in which we can do that. One is zinc acid reduction. So I can use a technique called zinc acid reduction. Essentially, if I take a haloalkene, so Rx, so R is my alkyl group, methyl ethyl propyl butyl, cyclohexyl, and X is my halogen, so chlorine, bromine, iodine, and so on. And I've mentioned this before. We don't, particularly in organic 1 and 2, we don't talk about fluorine. Fluorine chemistry fluoro-organic chemistry is a lot more complex than that of the chlorine, bromine, and iodine. So when we speak of halogens in organic chemistry, we don't typically mean fluorine. If I take a haloalkene and I treat it with zinc in the presence of aqueous acid, that generates the alkane plus the zinc ions and whatever X is minus. So if you look, this equation should be balanced. R, X, X, zinc, zinc, H, H. The overall charge on the left is 1 plus. The overall charge on the right, 0, 2 plus, 1 minus is 1 plus. So this is both mass balanced and atom balanced. So what this means is, I could, for example, take this compound and treat it with zinc and H3O plus. So typically, the H plus is a mythical species. H plus doesn't exist by itself, well, not normally, unless you're doing mass spec or something. In solution, it's H3O plus. So if I treat a haloalkene with zinc in aqueous acid, that generates my organic compound. And I could write the H here, well, in fact, I will for now, and I'll get zinc 2 plus and Cl minus. So overall, that's the equation, right? Organic chemists don't care what the inorganic products are. So although this is a balanced equation, I'm just going to write that, right? What is my organic reagent? My substrate? What reagents do I need? What is my product? So if I ask you, tell me a couple ways of making butane. You could say, I could make butane by hydrogenation of any one of these alkenes, of a diene, or of any one of those alkanes. That's hydrogenation. But I could also make butane by zinc acid reduction of a haloalkane. I could use this haloalkane, or I could use this haloalkane. Doesn't matter. Right? So the same methodology applied to one, let's use bromo maybe. The same methodology applied to one bromobutane, or 2 chlorobutane, or 2 iodobutane will give rise to butane as my product. It's a zinc acid reduction. Why is it a reduction? Well, this carbon is at the alcohol level. It's got one bond to a heteroatom. Same thing here. One bond to a heteroatom. Now, the product we're making has 0 bonds to heteroatoms. Those are at the alkane level. So I'm going from carbons at the alcohol level to carbons at the alkane level. That is a 2-electron reduction, which is why zinc goes from zinc 0 to zinc 2 plus, because it's lost 2 electrons. And what are those 2 electrons doing? Reducing the carbon from the alcohol level down 2 electrons to the alcohol level, to the alkane level. Right? So it's balanced. Right? So that's zinc acid reduction. I want to make a point here, and which is very important, and I should have done that here too. Instead of using H3O+, because H comes in several isomers, I could take the bromobutane and treat that with zinc and D3O+. This is deuterium, and give rise to that compound, or I could have taken the, well, just to mix it up a little bit, I could take this compound and treat that with zinc and T3O+ to make this compound. So I could introduce a single label into my organic compound using zinc acid reduction. And what do I mean by label? When I use a different isotope, one of the lower abundance isotopes, when I introduce that into the organic compound, that's often referred to as labeling, okay? Which we'll talk about in some more detail later on. And I should have mentioned it here too, because if, for example, I take this compound and I treat this with T2 and a catalyst, that's going to give rise to this compound. If I take this one and I treat it with, let's say, D2 and a catalyst, that's going to give rise to this compound. Okay? So when I use hydrogenation, D2, T2, I will do syn addition of D or T to the double bond. They will end up on adjacent carbons. So I will make the vicinal, that is the vicinal ditritio compound. Okay, ditritio, 2 T's. Vicinal means that they're in the same vicinity. They're on adjacent carbons. They're on neighboring carbons. So if I tell you, how would I make this compound? Right? Design a synthesis, outline a reasonable synthetic pathway using any reagents you want to make that compound. Well, you could tell me, here's what we do. Why don't we try taking either this compound, or maybe we could use that compound. If I treat this one with T2 and a catalyst, I'm going to get this. But if I treat it with zinc in T3O+, that's also going to give me exactly the same product. In other words, I'll get zinc acid reduction at both sides. Right? That is the essence of organic synthesis, which is a small part of organic 1, but it's going to be fully a third of organic 2. And understanding the reagents that you use to carry out the processes will be a big part of that. Okay, so we've talked about hydrogenation of alkenes and alkynes. We've talked about zinc acid reduction, and we've talked about introducing labels. In other words, isotopes of hydrogen into organic structures. While we're on that, let me talk about this for a little bit. So what is the importance of labeling? And again, when we say labeling in organic chemistry or biochemistry for that matter, when we say labeling, so this is DT labeling. What does that mean? And the answer is, it means essentially incorporating deuterium or tritium into an organic compound. Why would I want to do that? One of the nicest examples I can think of is, let's imagine we had an alien visitor. And the alien visitor was a scientist, which is likely to be the case. And the scientist is operating on the premise that humans, or life on this planet, consumes glucose with oxygen to make carbon dioxide and water. Okay? So their assumption is that we burn glucose to make carbon dioxide and water. How could they test that? Well, they could replace all of the H's in glucose by deuterium. So they can feed, they would capture some organism, hopefully not humans, they would capture some organism, feed it a source of glucose where they have changed the label, they've labeled the glucose with deuterium, so the organism then is going to be metabolizing deuterated glucose. And if they end up getting carbon dioxide and D2O, not H2O, well, then that would help to prove, that would be evidence in support of the notion that glucose is metabolized into carbon dioxide and water. In fact, what they could do, maybe in a separate experiment, is to label the carbons. So rather than go with carbon 12, the typical isotope, maybe they use carbon 13 and see if in the respiration they make carbon 13. And if that happens, well then surely enough, the source of carbon dioxide is the glucose. So in chemistry, and particularly in biochemistry, we often rely on the labeling of the organic substrate with either D or T, right, for the H's, or we can label the carbons, to follow particularly a convoluted mechanistic pathway. And we test a hypothesis by labeling the atoms, the carbons or the hydrogens, sometimes the oxygens, and as to provide evidence of whether or not a certain reaction, chemical or biochemical, is transpiring. So, and I will tell you, it is a very valuable tool in a mechanistic chemist or mechanistic biochemist's pathway, or even physical chemistry, to label atoms and then investigate the outcome. And you can do it both by looking at the product or by looking at the rate at which reactions happen. Okay, so from haloalkanes, we could use zinc acid reduction. Now, zinc acid reduction does one atom at a time. Hydrogenation will incorporate two Ds or two Ts or two H's on adjacent vicinal carbons. Okay. There is another method under zinc acid reduction which involves, say, via the organometallic. So, if I take a haloalkene and I treat that with a metal, let's say lithium, what I get is RLi plus, well, let me write the balance equation. So Rx plus 2Li will give rise to RLi plus Lix. That's the balance equation. I treat a haloalkane, and what's nice about this is, I should have mentioned that with the zinc acid reduction, this happens whether we're dealing with primary, secondary, or tertiary haloalkanes. That's also true for this reaction, right? Whether it's a primary all the way to tertiary haloalkanes. Haloalkane with lithium in the presence typically of dry diethyl ether. So Et2O, this is, remember Et stands for ethyl, that is this compound. So it's diethyl ether. So ETOET. In other words, Et2O. That's diethyl ether, which is sort of the diethyl ether. That is the common name for this compound. The IUPAC name would be ethoxyethane. So let's look at this a bit. First of all, it's balanced, 1R, 1R, 1X, 1X, 2 lithiums, 2 lithiums. It's also balanced in terms of charge. There's no charge on the left, no charge on the right. We are at a point in our organic career where we need to indicate what my conditions are. I'm using dry diethyl ether. What's happening here? And why is this important? Well, if you look, I have a carbon attached to a halogen. The halogen is more electronegative than the carbon, and so pulls electrons towards itself, creating a negative dipole on the halogen and a positive dipole on the carbon. So that carbon is an electrophile. Carbon is an acid. It's electron poor. But that's not true here. Because whereas heteroatoms are electronegative, sucking electrons towards themselves with varying abilities, right? Fluorine is better than chlorine, bromine, and so on. Metals, by their nature, are electron releasing groups. That's why the zinc in this reaction went from zinc 0 to zinc 2+. Metals lose electrons. Metals push electrons away from the cells. Metals are electropositive. So whereas the electrons in this bond were going that way, the electrons in this bond go towards the carbon. Which means now the carbon is delta minus and the metal is delta plus. So in this reaction, which is often called a metal halogen exchange reaction, or sometimes a metal halogen metathesis reaction, what I have done is I have changed the polarity of the carbon. I've gone from R delta plus to R delta minus. That inversion of polarity is often called umpolong. Umpolong, not oompa loompa, umpolong means charge inversion. I've gone from R delta plus to R delta minus. I have taken a carbon from being an electrophile or an acid into being a nucleophile or a base. I'm going to tell you, this chemistry, and this is called an organometallic compound. No, organic chemists are the worst when it comes to naming anything. I mean, we are bad. So even ignoring all of the complications of IUPAC, the way we name things is just very direct. This is a compound that has an organic piece to it and a metal. So what do we call it? An organometallic compound, right? Very unimaginative. This science of organometallic chemistry, which we will look at in more detail later on, is relatively young. It must be about 60-something, 70 years old. And the person who first sort of made the initial foray into this area of chemistry won a Nobel Prize for it. Because before that, carbon had two flavors. Carbon was either bound to other carbons, or it was bound to H. Right? It was bound to other carbons or H, or it was bound to a heteroatom. So if you're bound to another carbon, you have no dipole. So some people write that as delta zero, which is kind of a silly thing when I'm doing it now. So the carbon had no dipole. Or it's bound to a heteroatom and it has a positive dipole. That was it. There were two flavors. Carbon has no dipole, or it has a positive dipole. What Grignard, his name was Victor Grignard, what Grignard did is he created a version of carbon that had never been seen before. Carbon with a negative dipole. And that opened up a brand new ecosystem for carrying out organic reactions. And as a result, not surprisingly, he won the Nobel Prize for it. But organometallic chemistry is a rich, very robust area of organic chemistry. It's a wonderful hybrid between organic chemistry and inorganic chemistry. Okay. The reason, by the way, why this has to be dry is because, you remember this perhaps from the Gen Chem, electropositive metals like lithium, sodium, magnesium react with water. Some of them quite explosively. So if this ether, which ether is hygroscopic, it absorbs water, actually quite a lot, about 1 part in 7. If you left ether out in the open, in a couple of hours, it'll increase its volume by 1 part in 7 by sucking in water. If you add lithium or sodium to ether like that, it'll explode. Because the lithium reacts with water to make hydrogen gas, and that's very exothermic. So enough heat is generated that both the hydrogen gas, which is flammable, and the ether, which is flammable, burst into flame. Literally will explode. So we need to specify that this ether has to be dry. So ether is like the magic solvent for these organometallics. And interestingly enough, the other one that works very well is this compound, which is called THF, tetrahydrofurane. But if you look at it, it almost looks like ether, like the diethyl ether, right? It's got an O